Hi everyone. In this section, we are studying something really important, calculus. Before we jump into formulas, I want to step back and talk about what calculus is really about. Calculus was developed to solve problems involving two big ideas, change and accumulation. Everything we do in this chapter will connect back to one of those two ideas. Let's look at the first major problem that led to calculus, the tangent problem. How do we find the slope of a tangent line to a curve at a point? We already know how to find the slope of a line. That is just rise over run. But here's the issue. This is not a straight line. It's a curve. If I ask you, what is the slope right here at this point? It's not obvious. The slope is changing as you move along the curve. So how do we find the slope at that exact one point? This green line is called the tangent line. It just touches the curve at one point and matches the slope there. That question, how to find the slope at that one single point, is what calculus helps us answer. Now, let's look at the second big problem, the area problem. How do we find the area under a curve? If this is a rectangle, we could just use length times width, but the top is curved. There's no simple formula to this shape. So how do we measure the area under the curve that isn't straight? That's the second major question calculus was built to answer. These two problems, slope at a point and area under a curve, might seem different, but they are connected by one powerful idea. That idea is called a limit. We're not going to fully define limits today, but the basic idea is this. We look at what happens as something gets closer and closer to a value. Calculus is really about understanding what happens in that almost there situation. So in this section, we are going to start exploring how to measure change, how to estimate slope, and how these ideas lead to derivatives. Take your time with this section. These ideas are foundational. Everything in calculus builds from here. Now that we've talked about the big idea of finding the slope at a point, let's start building toward that idea. We cannot jump straight to the slope at one point on a curve. Instead, we'll start with something simpler. To estimate the rate of change of a nonlinear function at a point, we use something called secant line. The secant line is just a line passing through 2 points on a curve. That's it, nothing fancy. We pick 2 points on the curve and we draw a straight line connecting them. This purple line is a secant line because it passes through 2 points on the curve. This line gives us an average rate of change between these 2 points. Let's give these 2 points name. I am going to call this first point A, f of A. This just means the input is A and the output is whatever the function gives us at A, which is f of A. And the second point, we'll call it x, f of x. This means the input is x and the output is f of x. So now we want the slope of a line connecting these 2 points. the slope formula is change in y over change in x. Change in y is the difference between the outputs, which is f of x minus f of a. Change in x is the difference between the inputs, which is x minus a. And this is the formula of the slope of a secant line. This slope does not give us the exact slope at one point. It gives us the average rate of change between the 2 points. This is like driving from one city to another and calculating your average speed. You weren't going that speed the whole time. It's just the average over the trip. But remember the original question, how do we find the slope at exactly one point? Well, what if we move the second point closer and closer to the first point? As the 2 points get closer, the secant line starts to look like it's touching the curve at just one point. That idea is going to lead us to something called a tangent line. So for now, remember this. A secant line gives us an average rate of change between 2 points on a curve. In the next part, we'll see what happens when those 2 points come together.